Alright, hello class. Today we're going to be about optimization. So this basically takes what we've learned already about critical points and maxes and mins and just looks at application problems based on them. Okay, so this is when we take this idea and apply it to things, and that's where the word optimization comes from, because we're either maximizing or minimizing some sort of quantity. So maybe we're a business and we know what some sort of function we can create to model our profits. We, of course, want to maximize profits, or we could look at a function that is our cost over time, and we would want to minimize the cost. Okay, so I think the toughest part about these are the setup. Once you get them set up, it is literally what we've already been doing. So I will try to focus more on the setup and go from there. Okay, so let's take a look at an example, and I will kind of explain what we're doing as we do it. I think that might be the best way to proceed in this sort of topic. All right, let's start with a pretty typical sort of geometry type problem here. Let's say a rancher has 800 feet of fence for constructing a rectangular corral. One side of the corral will be formed by the side of a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions. So let me draw a picture of what we're talking about here. We have sort of a barn here. Okay, so here's our barn. And then we will have so one side of the corral is made by the barn, and then we have the fence here. It's going to look something like this. So we have the 3 outer or 3 exterior fences here, here, and here, and then 2 interior fences. So here's an interior fence and here's an interior fence that splits this into 3 rectangular regions. Okay, so of course we're not going to do that. So here in yellow, these are the fences. All right, so the question is now, what are the dimensions that maximize the enclosed area? So we want to maximize the area enclosed in here. So we want to maximize this. So there are a lot of ways that we could build this fence, right? We could make it very, let me do it here. We could make it very sort of wide, right? Or we could make it very sort of longish, like this, okay? Or somewhere in between. So each one of these possibilities in between here are going to give us different areas, right? So we want to find the possibility or the situation here that will give us the maximum area within our corrals. Okay, and then it asks, what is that enclosed area? All right, so let's talk about how we approach these problems here, okay? All right, so the first thing we want to do is find what's called the objective function. So the objective function, it's in the name, it's the objective of our problem. It's the thing we want to, or the quantity we want to optimize, okay? So the quantity that we want to optimize in this case is the area. We want to find the dimensions that maximize the enclosed area, right? So that's our objective. So that means the quantity we want to optimize is the area. All right, and the area, well, we want to optimize the full area here. So that's the area of a rectangle. We'll worry about the inner fences in a minute, but this is the area of a rectangle, right? So we want to maximize this area. Well, the area of a rectangle is length times width. Or I'm going to call this x by y. Okay, so the area is x times y. So this is the thing that we are trying to maximize here. We want this to be as large as possible. Now, the next thing we need to find is what's called the constraint. And the constraint is what allows us to do this. If we could just make any rectangle we wanted, well, we could just make it infinity large, right? But we are constrained. What is our constraint here? Well, this is sort of the restriction on our materials, what constrains us to not just build the largest rectangle in the world, right? Just make it as big as the planet Earth, right? We can't do that because we are constrained by our materials. And so that is where we have this. We only have 800 feet of fence, right? So that is our constraint. And we can usually make a constraint function that gives us this constraint, right? Because, let me clean this up a little bit. Yes, we're trying to maximize the area here, but our constraint in this case is the 800 feet of fence, right? We only have 800 feet of this orange fence to work with. So all of these added up need to sum up to be 800. And here's how we turn this into a function, right? Notice that the length y for our fence, we have 1, 2, 3, 4 y's, right? So we have 4 lengths of y and 1 length of x. Okay, so the amount of fence can only be 800 feet. So at the end of the day, this 800 feet must equal 4 y's plus 1 x. Or in other words, when we take the length y 4 times and the length x 1 time and sum them together, we must get 800 feet. That's the only amount of materials we have, and we would like to use all of them to be efficient, right? So our constraint equation is 800 equals 4y plus x. Right, so this is the constraint. Now, here is how we do this, okay? Now, we don't want to use implicit differentiation. We don't want to start diving into like related rates or anything, because these aren't rates that we're talking about. We're just trying to optimize the area. Okay, so how we do that is now we want to get the objective function into terms of a single variable, okay, using the constraint. So we're going to use this constraint to get the objective function in terms of one variable. Now, how do we do that? Well, we do that by solving the constraint by one of our variables. Okay, now in general, it does not matter which variable you solve for. So I would always choose the one that's simplest. Here, solving for x will be simplest, right? Solving for x, all we need to do is move that 4y over. If we solved for y, we'd have to move the x over, then divide by 4. So I think it's just easier to solve this equation by our 4x. So solve constraint, right? Solve for x in this case. So we'll just move the 4y over to get 800 minus 4y is equal to x. All right, now this right here, we're going to go back up to our objective function, right? And plug this x into the objective function. Okay, so now we plug this into the objective function. So I put the objective function here. It's a equals x times y. We're going to replace the x with that 800 minus 4y. So when we do, we get a, which now I can call it a of y, is equal to 800 minus 4y times y. Okay, now a of y, I could distribute this y across and say that that's 800y minus 4y squared. And there we go. This is the updated objective function. Okay, next up, a lot of these problems will ask you for the interval of interest. What the interval of interest is literally just where does this area make sense. If you think about, well, the area can't be negative. All right, so if we were to just set this equal to 0, and we'd get y is equal to 0 from this piece, and if we solve this for 0, we get 800 is equal to 4y, so y is equal to 200. So the interval of interest here is going to be 0 to 200. Okay, and that's because if we go below 0, we'll get a negative area. And if we go above 200, we'll get a negative area. So this is the only interval that makes sense for the area, because outside of this interval... All right, so let's suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 128 inches. What are the dimensions and volume of a square-based box, okay, with the greatest volume under these circumstances? Okay, so let's draw a little picture of what we're talking about. So first of all, I'm going to sort of ignore this first sentence for right now. The question is, what are the dimensions and volume of a square-based box? So a square-based box, if we draw a box with a square base, all right, what makes a square special? All right, well, when we draw a three-dimensional box, we have, say, length, width, and height. But the nice thing about a square-based box is that we'll have the same dimensions on the base, right? So we'll have a W by W by H. Okay, so that's our first thing that I would notice, is that, okay, we have two dimensions that are the same. Okay, so what are the dimensions and volume of a square-based box with the greatest volume under these circumstances? Well, greatest volume, that tells us our objective function. Okay, and our objective function is the volume. We want to maximize the volume, and the volume of a box is length times width times height, but in this case, length and width are the same, so we could write this as width squared times h or length squared times h. Either one will work here. Or you could call this x by y or whatever. The letters don't matter. In your online homework, it will likely tell you what variables to use. It will tell you which ones to label. Okay, but that's our objective function, w squared h. Okay, now the next thing we need is the constraint. Okay, and this constraint is given here. We're told that all baggage must be box-shaped. Okay, we've already come up with that. But with the sum of length, width, and height not exceeding 128 inches. That means that if we were to take the length plus the width plus the height, it needs to be less than or equal to 128 inches. Okay, so this right here is the constraint. Now this is what the policy says. The policy says that if we have length plus width plus height, it cannot exceed 128 inches. However, we don't want to consider anything less because we want to find the biggest box we can that will give us the greatest volume, right? We want the biggest we can get. So what we're going to set as our constraint, okay, is that our length plus width plus height should equal 128. Right? We want to hit that maximum, okay, in our constraint. So, and we already know that our length and width are the same, so really this I could go ahead and replace with w. So our constraint function is 2w plus h equals 128. Okay? Okay, now that we have the constraint, right, and the objective function, now we're going to solve the constraint for a single variable and plug it into the objective function. And again, it doesn't really matter which variable you solve for. I always just choose the one that takes the least amount of steps. So I'm going to move the 2w over. So I have that h is equal to 128 minus 2w. And we're going to plug this in for h in our objective function. Okay, so, all right, so our new objective function is going to be v is equal to w squared, now times 128 minus 2w. Okay, and if we distribute this, we will get 128 times w squared minus 2w cubed. And that is our objective function. Now, when they ask you for the interval of interest, I would use this factored version, right? So, right, because if you set this equal to 0, you get the w is 0, or here 128 is equal to 2w, so w is equal to 64. So the interval of interest is 0 to 64 because everything outside of this interval is going to cause this volume to be negative, which doesn't make sense for what we are trying to do. Okay? So, again, this is not something I'm that picky about, but it is something that you may be asked for. So, it is worth knowing how to do it to find the interval of interest. Okay? All right, next up. Now, we're ready to apply calculus. All right, so we're going to find the derivative, set it equal to 0, which we don't have to worry about undefined things here because we have a nice polynomial. Solve for w and get all of our dimensions. Okay, so we're going to take v prime of w, and that's going to be 256 times w minus 6w squared. I'm going to set this equal to 0 and solve for w, and we will do that by factoring. Okay, we can take out a 2w, so we'll end up with 2w times 128 minus 3w. Okay, and that's set equal to 0, so we get that w is 0, or 128 is equal to 3w. So 128 divided by 3 doesn't come out to be very nice, right? But it ends up, when you put it in a calculator, actually I don't need the approximate, it is 42.6 repeating. Now, how do we know which one we need? Well, 0 is definitely not going to be a maximum. That makes our volume equal to 0. However, if we want to really make sure, we'll take the second derivative to get 256 minus 12w. Okay, and when you plug in 0, you get 256, which is positive, which means we're concave up, which means we have a u, so we have a minimum at 0. That should make sense. We should have a minimum at 0, okay? It just means that we also have a horizontal tangent line at 0. Okay, then v double prime at 128 over 3. Okay, well, That's going to be 256 minus 12 times 128 over 3. That comes out to be negative 256, which is negative, which means we're concave down, which means that's our maximum. All right, so often I don't ask for this, all right, on, say, tests or quizzes or whatever, but it is good practice to just check to make sure. So this is our maximum, or we could use the 42.6 repeating inches. Okay, now that's just one dimension. We need to find the other by just plugging this value in to our W and solving for H. Okay, rewriting our H formula here. H is equal to 128 minus 2W. So we'll have 128 minus 2 times 128 over 3. So we get, shock, shock, 128 over 3 again. So we get 42.6 repeating inches. Okay, so it turns out that the most volume we can get out of this is basically a cube. Okay, 42.6 repeating by 42.6 repeating by 42.6 repeating. Okay, and that volume is going to end up being, sorry, I accidentally put squared. When we cube this value, we get 77,672.3 cubic inches. All right, and there we go. We have optimized this problem. Some of you may have guessed that a cube would be the best way to go here, okay? But we've used calculus to prove that it's true, to show why it's true. As we grow into what I like to call, say, adult math, right, into adult science, we can no longer just take a guess and expect people to believe us, right? If you're a really skeptical friend, you were trying to explain to him with this policy here that the best option is a cube, he might, or he or she might, want you to convince them. And this is that process here. This is how you use calculus to convince either your friend or, say, your supervisor, who's kind of stupid. We all have those, right? That this is the optimal way to go about sort of gaming the system, I guess. Okay? So, I will also say that not every example is going to follow that, right? You're not always going to get that cube that you might think. It's all based on what your constraint is. All right, saying that, let's look at another example. All right, so for our next example, here's something where this gets really important. Okay, and this is when it comes to cost minimization. All right, so let's say a water storage tank is built in the shape of a cylinder with a capacity of 32,000 cubic feet. The interior wall and floor of the tank must be cleaned and treated annually. Labor costs for cleaning the wall are twice as high per square foot as the cost to clean the floor. Find the radius and the height of the tank that will minimize the cleaning cost. So, unlike some of the other examples you might have seen earlier in this particular lesson, this one isn't about minimizing the cost to construct anything. It's more about minimizing the cleaning cost going forward. So the ideal shape here might actually be the most expensive to build, but in the long run will be the least expensive to maintain. These are sort of questions that companies, state municipalities, etc. have to answer all the time, okay? And this is where calculus comes in. All right, so let's talk about finding all of the things to sort of solve this problem. We'll start by drawing ourselves a picture. We're told that we have the shape of a cylinder. Okay, so here we are. Here's a cylinder. And a cylinder has dimensions height h, I'll call it h, and radius r. All right. Now, we want to find the radius and the height of the tank that will minimize the cleaning costs. So here's where we're going to have to sort of think a little bit about how we're going to set this up, because our objective function, okay, the objective function is the cost. Okay, so the cost, well, it's going to be how much it costs to clean the floor and how much it costs to clean the walls. So it's the cost to clean the floor plus the cost to clean the walls. Okay, now notice we don't know what the cost is, right? We just know that it costs twice as much to clean the walls as it does to clean the floor. Now, the floor, right, if we think about the floor here, that's just a circle. And notice that labor costs for cleaning the wall are twice as high per square foot. So that is your hint that this is area. Okay, so the floor, right, is basically pi r squared. That's the area of the floor. So the cost to clean the floor, okay, is completely determined by the area, since cost is determined by square feet. So it's not so much that we need to know the cost, we need to know how to minimize the square footage. Okay, so the cost to clean the floor is going to be completely determined by this pi r squared. Okay, the cost to clean the walls, well, the walls, actually let me use a different color here. If we split this, imagine a cylinder made out of a piece of paper and you slit it down the middle and spread it out. Okay, when you do that, you get this rectangle. So these are the walls all the way around. Okay, now the height of the rectangle is h, and this length here, well, that's the circumference around the circle, right? So that's 2 pi r. So the area of the wall, all right, is going to be 2 pi r times h. However, the cost to clean the walls is twice as much as it is the floor. So we're going to count it twice in the cost. So cost is double. So we can think about it as putting in twice the area, 2a. Okay, so that is what we will put in here, is this times 2. Okay, we could also do it just by itself and then divide this by 2, because it's, you could think of it as we take the cost of the walls and then divide it by 2 for the cost of the floor. In either case, we don't really know what that cost is. We're just giving ourselves an abstract representation. So when it's all said and done, okay, our cost function is, or in other words, our square footage function is the area of the floor, which is pi r squared, plus 2 times the area of the walls. Okay, so our objective function finally is pi r squared plus 4 pi r h. Okay, so this is what we want to minimize. So next up, we need to find the constraint. Might be easy to forget, since we did a lot of work to talk about the cost. But the constraint is given to us at the beginning here. We need to build a storage tank with a capacity of 32,000 cubic feet. This is the volume, and that's the constraint. Which is the volume. Okay, so the volume for a cylinder, well, a cylinder is just a circle that we add a height, right? So its volume is the area of the circle times the height. So it's pi r squared h, and specifically we know that that volume is supposed to be 32,000. Okay, so now we need to solve. So this is our constraint. Pi r squared h is equal to 32,000. And then we need to solve this for one of the variables. All right, now this might seem a little weird, but what I'm actually going to solve for is r squared. Or, well, I could actually, since if I didn't have r in both, I would do r squared. Let's just solve for h instead. Okay, so that's going to be the easiest. To solve for h, we just divide through by this pi r squared. Okay, so h is going to be 32,000 divided by pi r squared. Okay, and then this we are going to plug in to h in our objective function. Okay, now it looks kind of bad, however, some things are going to cancel here, so hopefully it will be not that bad. Okay, so let's go ahead and plug that into our objective function and see what we get. All right, so the objective function becomes pi r squared plus 4 pi r times 32,000 all over pi r squared. So here the pi's are going to cancel, and this r will cancel with one of these r's. And then we'll be left with, c of r is pi r squared plus, I'm going to leave this as 4 times 32,000 over r for right now. Actually, let's go ahead and write that as 128,000 over r. Now, you may be wondering what the interval of interest would be for something like this, and it turns out that it's really just r being positive. All right, so r just needs to be greater than 0, because if r is less than 0, well, that really doesn't make any sense, because we'll have a negative radius. But also, r can't equal 0 because we'll get blow up, right? So this function definitely has some sort of blow up happening, okay, at 0. And it can get as big as we want it to, really. We could let the radius continue to get larger and larger. The only thing is that when we do that, h will get smaller and smaller and smaller. Okay, so really our interval of interest is 0 to infinity, not including 0. Okay. All right, now it's time for calculus. Now we're going to try to minimize this function. And I'm going to start by rewriting this as r to the negative 1. Okay, so it's time for calculus. Now, I try to say this a lot, but in this module, right, this module for applications of the derivative, if you're not taking a derivative at some step, you're probably doing something wrong. Okay, so let's take the derivative. C of r is going to be 2 pi r plus, or not plus, but minus, when we bring the negative over, minus 128,000 r to the negative 2. Okay, now this does have an undefined critical point, because if we rewrite this as a fraction, 128,000 over r squared, r equals 0 causes this to be undefined. However, we are not considering that because it's not even in the interval of interest. Okay, so technically r squared won't be a critical point because, or sorry, r equals 0 isn't a critical point because it doesn't even fall in the domain of the original function. Okay, so all we really care about then is what causes this to be 0. All right, so we'll set this equal to 0 and solve. Now, my advice for problems like this, you could either multiply everything by the denominator that you have, and so that's what I'm going to recommend, is multiply by r squared, everything. Okay, so that you get 2 pi r cubed minus 128,000 equals 0. Okay, and now this is a much, much easier problem to solve here. We'll move that 128,000 over to get 2 pi r cubed is equal to 128,000. And so r cubed is 128,000 divided by 2 pi. Ugh. So that is kind of gross. And this just goes to show that these things don't always come out to be nice. All right, so this will come out to be 64,000 over pi, and so r is going to be the cubed root of 64,000 over pi. Cubed root of pi we can't really do anything with. The cubed root of 64,000 comes out to actually be 40. So we could say that this is 40 over the cubed root of pi. Okay, so this should correspond with our minimum, right? Mainly because we found a single critical point. If we want to really check it, we could do that with c double prime of r, which will be 2 pi minus 128,000. Actually, sorry, plus 128 times 2, so that would be 256,000 times r cubed, or sorry, to the negative cube, sorry. All right, now, this, if we plug in this value, if we plug in any positive value into this, this is going to be positive. Right, so it's basically positive for r positive. Okay, so that means that we are concave up. That means we have a smile. Therefore, this is a minimum. Now, typically, I'm showing this, but typically we don't really have to, because what ends up happening is that if you find a single critical point, which is one critical point, that is usually the one you're looking for, and it's going to be what you're asked to find, okay, in general. Although, if you want to check your work, this is the way to do it, okay? So, we've found r, but this problem, if we go all the way back up, is asking us to find the radius and the height of the tank that will minimize the cleaning cost. So, we found the radius. We just need to go back to our constraint to find h. So we will plug this in. We'll get 32,000 over pi, then r squared. And our r was 40 over the cubed root of pi squared. And actually, this 40 over the cubed root of pi isn't all that helpful, so I'm going to say that r is about, again, let me rewrite this, cubed root of 40 over the cubed root of pi, which ends up being, turns out to be about 27.3, and we're in feet here. And so in here, instead of this nastiness, I'll just put in the 27.3, and we will get for our height 13.7 feet. Okay, so let's actually write our final answer here. Here's all our work. Now let's just finalize this by saying, okay, the height is about 13.7 feet and the radius is about 27.3 feet. Okay, so it turns out that it's a fairly wider cylinder than you might expect. So that might not be the greatest like water storage, okay? But this would minimize the cost, and that's what this was essentially asking us to do. All right, so for this example, let's say a load must be suspended 6 meters below a high ceiling using cables attached to two supports that are 2 meters apart. How far below the ceiling, and this is X in the figure, should the cables be joined to minimize the total length of the cable used? Okay, so this one is one that really needs a diagram, so this one is provided for this problem. But we have a sort of a weight being supported by two cables that join together here and then go down and eventually reach the weight itself. So the question is, well, how far down do we need to go to use the minimum amount of cable, right? Should we make it a very shallow amount here? Should we make it this part go all the way down, right? So X can be anything between, well, 0 really. If X were 0, we'd be joining them together right there, or all the way to 6, where we use the full 2 cable suspension method. Or is the answer somewhere in between, right? Something like this. So this is what we want to deal with, and to find our objective, we're trying to minimize the total length. All right, and the length is going to be the amount of cable that we have here, plus the amount of cable we have here and here. Now these two should be the same length. Okay, we're not assuming that we're using more on this side than that side, so we'll call this L and this L. And then this length right here, well, that's going to be what's left over once we decide what X is. So that's actually going to be 6 minus X, right? Because the whole thing here is 6, this is X, then that's 6 minus X. Okay, so the total length is going to be 2 of these little L's, okay, plus 6 minus X. Okay, and we want to minimize this function, but first we need to get this into a single variable. Okay, and so what is the constraint? Well, this one's a little stranger than the ones we've seen before, because we aren't explicitly told the constraint, but it comes from right here. It comes from the fact that these L's are completely determined by X, because X is the height of the right triangle they make, right? The constraint comes from the fact that we have an X by 1, because we're splitting this 2 meters in half, by, let me match the colors here, L right triangle, right? So we have an X by 1 by L. Okay, so that means L is the hypotenuse of both of these triangles. Okay, and we have 2 of them. So L squared is going to equal X squared plus 1 squared. Okay, so that means L is going to be the square root of, I'm going to write it like this, 1 plus X squared. Okay, so this is the constraint, and we're going to plug that in for L so that everything, and notice we don't have to solve for L. Well, I mean, I guess we do. This is really a constraint. This is solved, but it's kind of pre-solved. But we're going to plug this in to our objective function to get our new objective function which is capital L of x is 2 times the square root of 1 plus x squared plus 6 minus x. Okay, so this is the updated objective function. And so now it's time for calculus. The interval of interest in this case is going to be 0 to 6. Right, because x could be 0 or it could be 6 depending on how we decide to set this up. I speculate though we're going to be somewhere in between instead. Okay, so it's time for calculus. All right, so we'll take the derivative L prime of x, and we're going to have 2, and this square root of 1 plus x squared is not going to be as pretty as what we've been looking at before because this is a chain rule. This is going to be, well, the derivative of square root of stuff is the derivative of the stuff, which is 2x, all over 2 times the square root of this stuff. Okay, or you could raise it to the negative 1, or to the 1/2 and do it that way. Either way, these 2's are going to cancel, but this 2 still sticks around. Derivative of 6 is 0, and derivative of negative x is 1. Okay, so L prime of x comes out to be 2x all over the square root of 1 plus x squared minus 1. Okay, now, since we do have a fraction, we should be concerned about what might make this undefined. However, 1 plus x squared is always going to be greater than 0, so we don't have an undefined critical point. Okay, so we just set this equal to 0 and solve. And so whenever you have situations like this, there's a lot of ways we could go about it, but I would start by moving the 1 over to get 2x all over 1 plus x squared on one side and 1 on the other, and then multiply this square root of 1 plus x over to the other side to get that 2x is equal to the square root of 1 plus x squared. And then we square both sides. Okay, and when you square both sides, you'll get 4x squared on the left side, and then the square root just goes away here, and you get 1 plus x squared on the right side. And all we got to do now is just move that x squared over to get 3x squared is equal to 1. So x squared is equal to 1/3. So x is plus or minus the square root of 1/3. Or if we rationalize the denominator, we'll have a root 3 over 3. That part isn't super necessary. Okay. And we're not going to use the negative 1 because it doesn't make any sense for x to be negative, so we'll get root 3 over 3, and that ends up being about 0.577 meters. So really, we minimize this situation by something kind of small, like 0.5 meters right here. So not right up on the ceiling, but close. Okay. So there we go. Now, this is one of those situations, I feel like I say this a lot, but where I cannot show you every single possibility that you will ever come across when it comes to this kind of stuff. But this method that we've started here, where you find the objective function, what are you trying to optimize? Right, that's your first question. Second question, what is the constraint? What constrains us? Then you plug that constraint. So you solve that constraint for one of the variables and you plug it in to the objective function. And then it is just find the critical points and analyze them as maximums or minimums. I did not actually determine that here. Okay, I'll leave that to you if you don't believe me that this does sort of satisfy what we're doing. Okay, but anyway, hopefully this does get you going on the homework because it's more about talking about the method and how we set these up. Once you get these set up correctly, they should just sort of follow I don't like to use the word routinely, but they should follow like we've been doing before. Okay, so as always, if you have any questions, feel free to reach out and let me know. And I will catch you all in the next one. Cheers.